In this video, we're going to be talking about weighted graphs and spanning trees. And these are just two topics that will sort of be introductory for some things that are to come. So first, a weighted graph is a graph in which each edge is assigned a value or weight. Okay, so let's just take a look at this graph. So here we've got a regular graph, order 5, right? V1, V2, V3, V4, V5. And there are various edges, and so let's go ahead and put a weight on each of these edges. So you can have integer weights like 1 or 3, you can have fractional weights, maybe 3/4 on this one, or negative weights, and they don't even have to be numbers. I mean, for this class we will just stick to numeric weights, but they don't have to be numeric weights, and they can be decimals. And we'll just round this out with these. Okay, so we had 8 edges, and so we have 1, 2, 3, 4, 5, 6, 7. Oh, this top edge is missing a weight. How about 4? Okay, so this is an example of a weighted graph. Now for us, at least, every time we talk about a weighted graph, every single edge will have a weight. So you're never going to have a mixture of unweighted edges and weighted edges. If one weight has an edge, then the rest of them should have an edge as well. So this is an example of a weighted graph. And the way that you talk about these things, you might say the weight of V1, V2. So remember, V1, V2 that's how we denote edges, is to list the vertices. So this edge is V1, V2, right? So the weight is going to be 1. So we use this little w, a lowercase w, to represent the weight. Similarly, how about the weight of V3, V4? What would that be? Well, you find V3, you find V4, the edge connecting them, -1/2. And similarly. So nothing fancy here. This is just the definition of a weighted graph is every edge gets some sort of value. And there are a lot of reasons where you might be interested in doing this. Maybe this represents the vertices are cities and the weights represent the distance between the cities. Now, of course, that wouldn't work here because we have negative distances. But maybe the vertices are customers and the weights are how much profit you will get from shipping X units of your product to them. So here you would lose money if you sent from this customer to this customer, but you would get a lot of money from sending this customer to this customer. So just like directed graphs, having directions on edges and having weights on edges are just two ways that you can get extra information into a graph. Okay, so that's weighted graphs. The second topic is a spanning tree. And a spanning tree, so remember you should have read the section on trees already, but a spanning tree is a connected graph, or in a connected graph is a subgraph, so remember what that means, a subgraph of the graph that uses every vertex and is also a tree, meaning it's connected and has no cycles. Okay, so let's just take an example here in pink. Draw 3 spanning trees of G, so here's G. So the first thing to remember is, right, subgraph means that all the vertices of our spanning tree have to match up exactly with these vertices, right, because it uses every vertex of G. Okay, so I've gone ahead and drawn 3 copies of the vertex set, 1 for each tree, right, because we know it has to use every vertex. And then otherwise it has to be a tree, which means that all these vertices need to be connected, and that there's not allowed to be any cycles in the edges that we choose. Okay, so for example, let me just draw one here. This is a spanning tree, right? All of these edges exist in the regular graph, right? These 4. All the vertices exist in the regular graph, so that makes it a subgraph, and this graph also is a tree because it's connected with no cycles. Okay, let's try another one. How about this one? Right, okay, so again, it's connected with no cycles, and each one of these edges is present in the original graph, which means it's a subgraph. Okay, so here are 2 spanning trees, so maybe you should pause for a second if you want and try and construct a third spanning tree that's different from these 2. And when I say different, I mean non-isomorphic. Okay, we ready? How about this one? And there are a lot of answers here, but that would also work, right? This edge, this edge, this edge, and this edge. Again, it connects all the vertices. All these edges are present in the original graph. And if you wanted to check that all of these are non-isomorphic, you can just consider the degree sequences. So for example, the degree sequence of this is 4, 1, 1, 1, 1. The degree sequence of this is 2, 2, 1, 1, 1, right? 2, 2, 2, 2, 2, 1, 1, 2, 2, 2, 1, 1. Right, and what's the degree sequence of this? 3, 2, so 3, and then 2, and then 1, 1, 1. Right, and non-isomorphic graphs, right, I mean, if graphs don't have the same degree sequence, they're certainly non-isomorphic. So here's an example of 3 non-isomorphic spanning trees, all of which go with this graph. And there are more examples in the textbook if you'd like to look at them, but this is an introduction to weighted graphs and spanning trees.